This is a series on linear algebra for quantum mechanics. In this video, we'll introduce the concept of basis vectors and inner products. In our previous video where we defined the vector space, we saw a few examples of a vector using a Cartesian basis. Let's look at that again with our vector v here equal to 2i hat plus 2j hat. Here, the numbers in front of I hat and j hat are our vector components, both equal to 2. I hat and j hat are our basis. They are directional indicators. In Cartesian coordinates, I hat and j hat are used. Here we show the vectors themselves. You can recognize them with their little hats. Be careful not to confuse the unit vector in the x direction with the imaginary number I equals square root of -1. They are unit vectors because they have a magnitude, aka length, of 1 unit in this coordinate system. And recall that the way that you compute the norm is using the square root of the sum of the vector components squared. The vector components just tell us how much to mix in of each direction to get our vector v. In a particular basis, we don't change the vector. We're choosing one that's convenient for us. We could change the basis to another system, such as a spherical coordinate system. When we change basis, the components will change, but we're still talking about the same vector. Here, v is a linear combination of our basis vectors I hat and j hat. We take each basis vector, multiply it by a number, and add the results together. In 3D Cartesian space, we have I hat for the x-axis, j hat for the y-axis, and k hat for the z-axis. If there were a vector that could not be written down as a linear combination of a particular set of vectors, we would say that vector is linearly independent of that set. So for example, with just I hat and j hat here, we cannot represent a vector that is in the z direction only. So that vector that's in the z direction only, we would say is linearly independent of I hat and j hat. Here, I hat and j hat are linearly independent too. We cannot represent I hat by scaling j hat. But the linear combination of I hat and j hat covers the entire 2D space. We can represent any vector in the 2D Cartesian space using a linear combination of these two vectors. We say that they span the space. And when we have linearly independent vectors that span the space, we have a basis. This basis is an orthonormal basis. The ortho part of that means they are orthogonal to each other, which means they are all perpendicular to one another. The normal part means that they are all normalized, which means they have unit magnitude. That is an orthonormal basis. You're probably familiar with the dot product, also called the scalar product because the result is a scalar. Here we're going to multiply our vector v from before with a new vector w. The result of the dot product is the sum of the multiplied components in the same basis. Another way of writing the dot product is equal to the norm of each vector multiplied by the angle between them. Here, theta is the angle between the two vectors. So if two vectors are parallel, the angle between them is 0. Since the cosine of 0 is 1, then the dot product is just their norms multiplied together. If two vectors are perpendicular, as in this case, the angle between them is 90 degrees, and cosine of 90 degrees is 0, so the dot product is 0. If the dot product is 0, the vectors are linearly independent. An intuition here for what the dot product is telling you is how similar are these two vectors, or how much of v do I get when I walk along w. And from this equation, you can also see that a vector dotted with itself just gives the square of the magnitude. Let's go back to our vector v in a 2D Cartesian basis, here made generic with the vector components a and b. Here we're showing in Dirac or bracket notation what the vector is represented as, which is a ket. We can also represent our ket here using a column vector, where we write our vector components into the column. And here we're making a choice of basis, which we'll want to be consistent about as we do any computations using bracket or Dirac notation. So we've seen the ket. Here is the bra. Here is a bra for u, and it is represented here as a row vector, where we're taking the complex conjugate, that's the star, of c and d. So recall that the complex conjugate of a number z with real part x and imaginary part y, the conjugate is just flipping the sign of the imaginary part. So instead of plus iy, we have minus iy. So now, armed with our knowledge of bra and kets, we can now compute the inner product, which is the general form of the dot product in a vector space. Here, a complex vector space, because in quantum mechanics, our vector components will often contain an imaginary part. We write the inner product here as a row vector multiplied by a column vector, and we compute the expression on the right-hand side by just doing regular matrix multiplication. So we get the complex conjugate of c times a plus the complex conjugate of d times b. Let's do a concrete example using the two vectors here, v and u. Here we'll use v as our ket, and we'll use u as our bra. So when we compute the inner product, we'll need to take the complex conjugate of the components of u. And the complex conjugate of the components of u is, again, just flipping the sign of the imaginary part of the component. Once we compute the conjugate, we get the following, again, just with the signs flipped. And then once we compute our final answer, where we multiply through by 2 for the x component, and we multiply I by I together, which gives us -1, pass the negative sign through, which gives us +1, we get 3 minus 4i. So in this video, we learned about linear combinations, linear independence, orthonormal basis, and how to compute inner products. Thank you for watching, and I hope this was useful.